Oh, thank you very much. Thank you very much. So, see if we can get the screen share going here. But yeah, thank you for that intro, Tim. It has been great to work with you over the last year. I absolutely agree. We've done some good things. Um, so it looks like chat. I'm going to need. There we go. Share desktop. All right. We see my cover slide there. Good. So, right, escape velocity, better metrics for agile teams. This talk is really an abstract from my book called Escape Velocity, and hopefully folks will find it useful. I want to start off. I want to actually ask the audience, and we're going to try something with Menti here. We think about velocity. Right. It's a really commonly used term. And I'm curious to find out from people in the audience, what does velocity do for them? So if you will indulge me, have this come up in a second here. If we can go to menti.com and the code is 115318, should be up there on the screen. And there's just 5 questions. I'm just asking you to rate them from, strongly agree to strongly disagree. In your experience, does velocity provide these things for you? We'll give us a few minutes. All right, we're starting to see it move as we get more answers in. All right, and we're starting to see it kind of take a fairly consistent shape here. Now, this is on a 5-point scale where, 5 is that we strongly agree, and basically a 1 is that we strongly disagree. And we'll notice that most of these are, a couple points away from strong agreement. So the best we're getting is neutral, and some are actually much closer to the negative. And this kind of leads us maybe to the conclusion that while we all seem to use velocity as a general statement, velocity's almost useless. Right? For most teams, the issues are, their velocity is not stable enough. So they can't actually use it reliably for short-term predictions, much less long-term predictions. If it is stable, it's often actually disconnected from deployment or delivery. So we're counting velocity because the development work was done. Maybe we think it's ready, but it's not actually in production. And so we're completely losing any of that data in terms of how long does it actually take before the customer gets it, which really means that we can't actually answer the question, when will customers have this very reliably, right? If it is actually connected to deployment and delivery, which for many teams, again, it's not, it rarely accounts for any other aspects of the process, right? It talked about kind of the we can't see what the cycle time is between any of the different phases. We can't actually see usually the wait time between when a request comes in and when we actually start to work on it, because oftentimes it actually begins when we start the work, in terms of development, not actually, the request. And even when all of these things are happening, velocity doesn't do a very good job of telling us anything about whether or not the work that we're doing is making the customers happy. And it doesn't really tell us very much about any of the maybe issues that the team is facing in that kind of delivery process. So I think with this, why is velocity nearly useless? And I think in order to understand that, we have to actually think a little bit and talk a little bit about what is velocity. Now, if you ask this question to a broader audience or to a group of friends or whatever, there's a number of answers that come back, but almost every single answer fundamentally boils down to the same thing. Velocity is, first and foremost, is work units over time, right? You have some amount of stuff that gets delivered in some period of time, whether that be sprints, iterations, or just a week in a continuous flow system. Doesn't matter. What we're looking at is how much of this stuff did we get done in this chunk of time. Now, for those of you that have studied any physics, high school level type stuff, you know that that's actually just speed, right? Units over time is speed. Velocity is a vector. It actually needs a direction. So when I think about velocity, I think about it as work units over time towards delivery of value, right? So that fundamental definition of velocity. But there's more to it than that. Turns out velocity is also a lagging indicator. Now, lagging indicators tell us what happened. They're actually fairly good for confirming long-term trends, but they're actually not very good predictors, right? So the graphic that we have up here is an unemployment line. Unemployment is a lagging indicator. If the unemployment rate is rising, then the economy's actually been doing fairly poorly. We know how it's trending, but we don't actually know where it's going to go next. And if we want to really kind of remediate the issue, history's kind of proven it's not very effective to create jobs programs to try and fix unemployment if the things that are hurting the economy don't also get remediated. And most of the jobs programs in the past have worked for a period of time. And once the funding runs out, we kind of see an additional smaller recession. What else is a lagging indicator? So if we look at sales, right? So let's look at this. This is a quarterly sales revenue for a subset of retailers in the US. When we look at this, I'm going to zoom in on it. You can't really take a look at any given quarter and its end results, and from that forecast what the next quarter is going to be. If we used our standard kind of velocity approach, and at the end of Q1, we said, okay, well, sales was this much. What's sales going to be in Q2? We'd guess this much, but it's actually going to be more, right? What we can use this for is we can confirm long-term trends. We can confirm from this that fourth quarter sales are typically much, much, much higher than the other quarters. And we can predict that first quarter is going to be the least, right? So we can see that trend, but we can't forecast very well with it. What else is velocity? I think it's important that we remember that velocity is actually a fundamentally simple measure of a very complex system, right? The graphic up here is a kind of a standard, iterative, scrummy, whatever you want to call it, cycle. And we have a number of inputs. We have a number of ceremonies, processes. We have a number of different people that are involved. There's all kinds of motion and activity and decisions and things that are happening. And then at the end of some time period, we take a measure, and that's our velocity, right? It is the output, a very simple measure of a relatively complex system. So velocity is a lagging indicator of a complex system. got thinking about this, like, all right, well, I understand that if it's a lagging indicator, it's not a very good predictor. And if it's from a complex system, maybe it doesn't represent all of the things. If I think about this from a metaphor standpoint, what else do we know of that is a lagging indicator of a complex system? Maybe if we can equate this with something that we commonly know, we can reason about it a little bit. And it turns out that your body weight is a lagging indicator of a complex system. I think we could agree there's inputs, there's outputs, there's activities, there's all kinds of complex and strange things that happen in there. And every once in a while we step on a scale. That's our body weight. So let's think about this for a bit, right? What are things that affect body weight? So it's not just about the food that we consume, but it could also be our diet, our exercise, our genetics, our physical health, our mental health, the environment that we're in, the type of work that we do, the stress levels that we have, our social network. Yes, our social network, not Facebook, but the people that we hang out with most often, the people with whom we most closely associate, actually materially affect our body weight. Now, does a given body weight actually mean that you're healthy? And the answer to that is no. We can't tell from body weight alone if someone is healthy. If I told you that I know someone named Pat and Pat weighs 400 pounds, and I asked you, is Pat healthy? Well, you don't know if Pat is a center for a pro football team or a 12-year-old boy. You don't know what Pat does. You don't know enough about Pat. The body weight is insufficient for us to know if that individual is actually healthy. And the same is true for velocity. For any given team, if I told you what their velocity was, you could not tell me if that team was actually behaving in a healthy way. Even if I told you that it was 0, with a 0, you could probably say, yeah, something seems to be wrong, but I'm not sure. Maybe it turns out their velocity is 0 because they don't track it. Now, let's go back to body weight. Think about the different ways that you might choose to lose weight, right? Let's say that you wanted to lose 10 pounds, 5 kilos. There's a number of things that you could do here. You could reduce your caloric intake. You could make a change to your exercise routine. You could look at your sleep patterns, maybe get more sleep. You could just cut back on certain foods. I've known people who have done things like simply stopped drinking soda and changed nothing else in their life. And that's had a material impact on their ability to, regulate their weight. Right? But what else could you do if you wanted to? If you really were focused on, I need to lose this weight, and my goal is to go from where I am today to 10 pounds less, from where I am today to 5 kilos less. What are other things that you could do? Well, you could stop drinking all liquids. You could consume nothing but amphetamines. You could smoke crack, or you could sever a limb. Now, the point here is relatively simple. Moving the metric in the right direction doesn't necessarily improve the health of the overall system, and it may in fact hurt the health of the overall system. We see this often with velocity. How do teams go about increasing their velocity when they suddenly understand that there's an expectation, a need, a desire, a demand, a request that velocity increase? Well, some teams will do things like they'll look at limiting their WIP. They'll consider reducing their batch size. They will look at how they better manage dependencies between themselves and other teams. They might even consider reorganizing a bit to reduce those dependencies and then limiting WIP and reducing batch size. But you know what else teams can do? They can skip testing altogether. They can cut corners on internal quality, or they can work more hours per week until they burn out. They could, in fact, increase all of their estimates. That's the easiest way to increase your velocity. just start estimating higher, right? And the point is the same. Moving the metric in the right direction doesn't necessarily improve the health of the overall system, and it may even hurt it. Good intentions or not, when bosses set goals or ask for improvements and indicators like this, velocity, they're almost guaranteed to create problems rather than benefits. There's a law in economics which is actually applicable across multiple industries, but it originated in economics. It's called Goodhart's law. Specifically, it states that any observed statistical regularity will tend to collapse once pressure is placed upon it for control services. Right? Any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. All right. In other words, when you take a metric that is a trailing indicator and you set a target for that metric, the metric no longer means what it once did, and therefore the target doesn't mean what you think it does. By setting a goal for a metric like that, you've actually changed the system. And what you're measuring and what it means has changed in accord with that. Now, when we do this, we often see interesting behaviors in the environment, right? People are incentivized to hit these goals, so they will hit the target by whatever means necessary. We end up with something that's called perverse incentives, which ends up being an unintended result. It's an unintended result. It's actually oftentimes contrary to the interest of the incentive makers. So, if we set a goal for, hey, we want to increase velocity. What's going to happen? What's probably going to happen is quality is going to go down, or the team is going to burn out, or we're going to start hiding certain types of work or other sorts of behaviors. They're actually contrary to the interest of the individual that made the incentive in the first place. If we ask teams to, we're going to reward them for cleaning up bugs, one of the things that often happens is we start getting into wasteful debates about whether or not this is a misfeature or bug, and more bugs are getting reported with these weird nuances in them where it's really all the same defect, right? We're actually driving waste into the system when our intention was to improve quality. We've actually slowed down delivery, right? So there's an interesting thing that happens here. Oftentimes I will hear managers, leaders say, and I'll even hear employees say this, you know what, the problem is actually that employees just game the system. It doesn't matter what you do. The employees just game the system. Well, I want to put this out there, and I want to get this straight with you folks right now. Managers game the system by setting goals for measures and metrics. The rest of it is just natural consequence. This isn't people gaming anything. You changed the system. The system responded exactly as it should have in accord with what happened there, right? Every system is perfect. It produces the exact results that it is designed to produce. You're designing the system. If you're getting these results, it's just natural consequence. Now, when we look at teams, how is velocity used? And if we think about, here's this metric, it seems like almost everyone tracks it in one way or another. And if you don't call it velocity, you probably call it throughput, although there's some baggage inside of velocity that doesn't necessarily exist inside of throughput. But fundamentally, how do we use velocity? What's its primary use? And if we talk with folks, typically there's a few things that we use it for, maybe really only a couple, which actually end up boiling down to one. It's usually used to plan an iteration or a sprint, right? We either take the prior velocity and we forecast the next iteration as a result. Sometimes we take a rolling average over 3 or 5 iterations because we want to account for variance, and then we forecast into the future, right? This is the primary use. Secondary use that I see sometimes is trying to track a release. So we'll look at a big chunk of work. We've got 130 stuffs that need to get done, 130 units that need to get done. Can we get it done 13 weeks from now? Well, gee, let's look. Our velocity has been an average of 10. 130 divided by 10 is 13. Looks like we're going to make it, right? This is fundamentally how velocity gets used kind of across the board. So we get asked. This is probably one of the most common questions that we get asked. I'm going to need to know how long this feature is going to take. Now, it's funny to me because this is oftentimes the question that gets asked. Nobody cares how long it's going to take. No one does. What they actually want to know is when will it be done? And these are not actually the same question at all. Now, if we're using velocity for forecasting, I'm going to argue that really we're only sort of forecasting. Right? We take an average, let's say, of the past few iterations. We divide it into our current guess for the work that needs to be done. And maybe we got a really cool graph that looks something like this, and we can actually put a trend line on it. And then we can see that, you know, the point where the trend line crosses the remaining work, that's the point at which we're actually going to be done. And that's the date that we communicate. Now, I'm talking with teams, oftentimes I ask them, are these forecasts accurate? The answer is usually no. They don't tend to be particularly accurate. Even if we might imagine they're precise, they're not accurate. I don't think they're even precise, right? Are they definite? Well, no, they're absolutely not definite. Okay, definite's pretty extreme. Are they probable? Well, by a formal definition of probability, of course they are. There is some probability that this is an accurate forecast, or there is a probability that we will hit that particular date. So the question really starts to become not are they probable, but how probable are they? Now, we don't have enough information when we're using just velocity to know exactly how probable we are, the estimates are. But we can do a little bit of work here to get within a reasonable range. So how do we actually get them to probable? How do we get them to a place where we know how likely that date actually is? I think there's a better way to forecast in general. And the way that we do this, you need some information. So the first thing you need to know is your velocity and your backlog size. So that's pretty familiar, right? That's what we've always needed to know. If we're going to do some kind of a larger scale forecast, we've always needed to know how much work is remaining and what's our velocity-ish. All right. What else do we need to know? Well, we need to know the start date. And we need to know something called split rate. Now, this is optional, and we'll go through this a little bit. Split rate's actually optional. To do this, you really only need the first three things, and you'll see a significant improvement. So I'm going to ask you right now, looking at the data that's on the screen, we have, this is our prior velocity. Our backlog size is 130 ducks, units, points, whatever you want to call them. It's 130 somethings, right? And our velocity is 11 somethings, 10 somethings, 9 somethings. Our start date is today. Can we get this work done by August 8th? To help you out, August 8th is 13 weeks from now. Do we think we could do this? Well, to answer this, I'm going to use a technique that I recommend for all teams. Some of you may be familiar with this. More and more folks are. I'm a big fan of the work of the folks over at Focused Objectives. Sorry. They have a series of tools around forecasting and other metrics and analysis that are publicly available. The link to them is right there, focusedobjective.com/w/support. From there, they have a whole list of resources, including a couple different types of forecasters. I'm going to dump out of the presentation in just a second. We're going to see a live version of this forecaster. Here's a quick snapshot of kind of what it looks like. And then let's see if I can get, okay. I am hoping you are looking at my Excel sheet.
We are.
All right, thank you very much. Okay, so this is exactly the data that we had. The start date is today. We have our work to be done is 130 somethings, and our average velocity, you remember 11.10.9 or 11.9.10, whatever it was, the average is 10. What this tool does is it takes that information, it takes that data, and it simulates a actual series of iterations. So it says, all right, your range is anywhere from 10 somethings to 10 somethings, 10 points to 10 points. So I'm going to take some number in that range, turns out 10, and I'm going to subtract it from the overall work. That's one iteration. I'm going to do that again. I'm going to do that again. I'm going to do that again until I get down to there's no work left. And that helps me figure out when might this work be done. Now, what it actually does is it runs that simulation 500 times, plots the outcomes on a histogram, and then can calculate a probability based on that. Now, of course, what we're looking at right here is, so this graph over here shows us probability. Based on the data that we have somewhere between a 0% and 100% chance that this work will be done in 13 weeks. This is our velocity math, right? This is what we normally do. We take some average or some number and we divide it into another number and we go, there it is. Now, let's take a look at this. Remember that the velocity over the last 3 iterations, while it averaged 10, had a low of 9 and a high of 11. So let's just change that. And nothing else about this. We change that, what happened? Well, what happens is we now suddenly see that we have somewhere between a 0 and 55% probability of getting it done 13 weeks from now. And we actually have a much higher probability of getting it done in 14 weeks. So we're off by, we're off by a week using this. But what's really important about this is using our standard techniques, it turns out that the probability that we're going to hit that date for most projects ends up being under 50%. The math that we've been using to forecast our projects is worse than a coin toss in actual probability that we're going to hit that date. As soon as we start to look at, so this right now is based off of an estimate. It turns out that I can actually record my velocity, my throughput over several iterations. And what this tool will do is use the last, I think, 12. And so now we start to see that there's a variance in the velocity. This tool will actually take that into account. So it changes the logic when we move from an estimate to using actual data. When we use an estimate, what it does is it chooses a random number between the ranges that we've given it. for each iteration that it simulates. When we use the actual data, it doesn't choose a random number in the range of the data, right? So it's not choosing a random number between 6 and 11, let's say. What it's actually doing is choosing a random number, 1, 2, 3, 4, 5, 6, 7, let's say it takes 12, it considers 12 iterations. It chooses a random number between 1 and 12, and then takes this, whatever value corresponds to that. So what it's doing is, if most of your iterations are, 10, but you got a few outliers that are 3 and a couple of outliers that are 17, it's actually running a simulation that represents that kind of distribution of velocities over a period of time. And now we see with the data that we had that our 13 weeks is actually at a 45% probability. And if we really want a high confidence level, we're actually going to get this done sometime around the end of August or the beginning of September, as opposed to, what we're promising is the beginning of September, and we've only got a 45% probability that that's actually going to happen.
Hey, Doc,
Yeah.
we have a question from the audience.
Okay.
This is, do you adjust velocities based on known scenarios in upcoming sprints, like holidays, PTO?
So it ends up that it's really not necessary to do that. I get it, and a lot of times this is some of the complication that starts to happen amongst all these things. As we start thinking about things like, oh, but next iteration someone's going to be on vacation, and then because this is using a fairly long horizon. If you're using the actual data, it tends to account for those types of weeks happening. So it's really not necessary to start thinking about resource loading. Now, if you've got really wild variance in the staffing on the team, that's a whole nother issue that really needs to be directly addressed, because that is going to adversely affect your ability to forecast no matter what. And it really kind of starts to eliminate our opportunity to use systems like this, and starts moving us back towards other systems that are not nearly as effective. All right. So we noticed we've now got a better way of forecasting, right? We now got a better way of being able to say, hey, here's where we actually are. Here's the probability of us hitting particular dates. And what I've seen with this is much, much better conversations. So, the team hears, hey, we're really excited about this feature. We'd love to have it by, the first week of August. We want it before the 15th. And we can now go back and say, you know what? The 15th has somewhere between a 60 and 70% probability, but the following week has an 85 to 95% probability. And the business gets to now, we now get to make decisions based on, kind of risk profiles, right? Like, all right, 45%, that's too much risk. I don't want to start, over communicating a delivery that we've got less than a 50% chance of hitting. But maybe I'm willing to take the risk around 60%. I'm definitely willing to take the risk around 90%. So we can have a much better conversation then. But one of the things that we noticed as we looked at this history, and one of the things that's very common for teams is these variable velocities. Your velocities all over the place. And so what do you want you to do? Well, we're going to need you to fix that, right? And if you could fix that, then the forecasting would get even better. Now, we're going to do another Menti. I want you to take a look at this chart for just a minute. What this is 10 iterations. It is the velocity of this team over the last 10 iterations. And we'll switch over to the Menti in just a second. In fact, I'll go ahead, for those of you that still have it open, I'm going to move us to the next question. Get this picture in your head. Take a look at this chart. Think about it for a little bit. And the only thing I want you to tell me is, what's wrong with this team? So again, it's menti.com. It's the same. It's the same code 1153.18. And now what we're curious to hear from you is, based on that velocity chart, what problems does this team have? What are they suffering from? Inconsistent estimates. Nothing's wrong with this team. Their stories are too large. Inconsistent. Yep. It's impossible to tell. They're not able to finish stories in a single sprint. They're unstable, don't have enough backlog. They're having a problem with team commitments. Big bang completes after some iterations. Yep. So a lot of folks are saying things like, hey, they're inconsistent, but we can't tell why. Or that inconsistency is in fact the problem. Inconsistent estimates, stories aren't truly development ready. They got a bad scrum master, right? They're carrying work forward from sprint to sprint. I like this one. Likely there's too many things to give a single answer. Sure. They're not breaking work down into chunks to be completed by an iteration. Right. So we have a lot of speculation around what is actually wrong with this team. They've got a lot of technical debt. There's a good one. I like that one. All right. Now, I think most of us know this dude. So Dr. Deming tells us that, like, look, it doesn't matter. It doesn't matter what the goals are. Don't set quantitative goals. Fix the methods by which goals are attained. Try and look at causal analysis. What might be contributing to the adverse outcomes that you're getting, and focus in on those things. So, if we want to stabilize velocity, we don't focus on velocity as the metric. We've got to look at other things that inform us enough to be able to understand what it is that we need to actually remediate, what it is that we should be, going after, if you will. So there's a lot of things that I think are common causes to variable velocity. We're going to go through a few of those today, and we're going to talk about some metrics that we can use to help us maybe monitor, and one, see if those things are causal factors, and two, if they are, we can actually maybe see if they're getting better, getting worse, staying the same. Right. So I think one of the key things, and this got mentioned as technical debt, I have been moving away from the technical debt term as a metaphor in general. There's a lot of reasons for that, but fundamentally, it's become so overloaded, it doesn't mean anything anymore. And it certainly, for most of the industry, doesn't mean what it originally meant. What it originally meant was actually quite healthy. It was clean, well-tested code wherein what we've implemented doesn't match what the customer actually wants or needs. That was technical debt. Today, it means all kinds of garbage. So let's call it just deferred maintenance, right? These are the results because we didn't have time to clean the code, or we thought we didn't have time to clean the code. We made the choice to not refactor, or maybe we didn't even know how to do that. We made the choice to not upgrade infrastructure and not pay attention to the evolution of the underpinnings of the technologies that we're using, right? And all of these things ultimately start to really gum up the system. They cause it to move slower and slower in the name of speed. And then we start to see things where, we end up buried in an iteration around trying to get this one little thing wedged into this code. And then the next iteration, boom, lots of delivery, right? So this is one of the things that contributes to variable velocity. As I said, it gums up the system. It causes it to move much slower. So what do we want to track? If we want to track this and see, one, does it actually exist for us? And two, then can we determine if it's actually getting better or getting worse or staying the same? One of the things I look at and recommend for a lot of teams is a relatively simple measure of code complexity. There are different measures of this. We can get into debates over them: psychomatic complexity, ABC complexity. These are known by different names, et cetera. Fundamentally, all these things are are a measure of the logic branches in the code. How many different conditionals are in there? How many different paths are there through the code? Let's take a look at this. So this is a strictly linear program. So into the method, out of the method, no conditionals. That typically has a complexity of 1. Things like a do, until, a while, a for. So these are logic loops. All of these have complexity of 2. When you find a case statement in the code, that tends to have a complexity that increases for every one of the options. So if we've got 3 options, it's got a complexity of 3. If we've got 4 options, it's got a complexity of 4. The exception there is if every one of those options or some of those options have exit statements, it actually increases complexity more. So this is all just a measure of the paths through the code. Why does this matter? Why would we want to measure this? Well, it turns out that there is a positive correlation between code complexity and defects. And this is universally true. The higher the complexity, the more likely the method is going to have high coupling, low cohesion, the more likely that code is going to actually have bugs in it. Now, I can't tell you that a complexity number of 7 results in 1.4 bugs per iteration. What I can tell you is the higher the complexity, the more bugs you're going to find. Those two things are positively correlated. In addition, as I kind of mentioned, the higher the complexity, the harder it is to understand the code, the harder it is to actually manage and maintain that code. And the more that happens, the more likely when we get into that area of the code, the slower that we actually move. So this is an easy thing to measure. It's a static analysis. Almost every tool out there will measure this for you. What you're looking for then is how is it trending? Is the complexity going up? You probably don't want that to happen under most conditions. Is it staying the same? This might be fine. Is it decreasing? This may be and is probably what we want to have happen for the code. There are circumstances, and this is important with all metrics, it's all about trending. It's not about the current value. And you need to make sure that the trend is consistent with your strategy. So the reason I say this is there are techniques for cleaning up code that will actually increase the complexity for a period of time. Then there's a moment where we remove all of the old stuff and only new stuff exists. So you may have heard of things like decomposing a monolith into microservices. Sounds like a lot of words, but it basically means I'm taking something that's really kind of coupled together and I'm starting to write new pieces that represent all the little activities. As I'm doing that, the complexity of the overall application goes up. Then when I'm ready, I can take out all the old code, the complexity goes back down. So during that effort, the trend is actually going up even though complexity is bad. So we always have to remember it's about trending, and it's about that trending being consistent with your current strategy. Is it doing what you expect it to do or want it to do? If it is, fine. If it's not, then dig in and take a look. All right, what else can we look at kind of universally for quality of code? And I've chosen many of these metrics intentionally for their universal applicability. So I have other metrics that would be germane to Java projects, but would not make any sense for a mainframe project, whereas most of the stuff that we're talking about here today is universally applicable. So the next thing to look at is escaped defects. Now, this is the count of defects found in production. My opinion, escaped is an unnecessary word. The only defect is an issue that's in production. If you find it in QA, that is a part of your internal process. That is not a defect. That is actually evidence that your processes are working. But some organizations count those as defects. I don't care. What I'm talking about is defects that are found in production, so we'll qualify them as escaped, right? Now, the thing with escape defects is this number by itself, so here we're looking at escape defects over time, could be misleading. It's not enough information for us to know if things are getting better, worse, or staying the same. And that is because, remember, we probably have variable velocity or variable throughput. And so we need to actually look at defects that have made it into production, contrasted against how much work was actually delivered in that particular iteration.
Hey Doc, we had a quick question from Sanjay.
Okay.
Do you think automation, things like BDD, TDD could help with this aspect?
Absolutely. So I think they happen. I think they help tremendously, and there's a number of reasons for this. So TDD especially is it's not about testing. You happen to test to do it, right? People a lot of times call TDD test-driven development. I refer to it as test-driven design. Many people in the industry do refer to it as that. And the reason that we refer to it as that is it's actually a design technique. When I write this micro test, and then I have to write code to make it pass, and then I write the next micro test, I have to write code to make it pass. As a natural byproduct of that, I'm constantly writing code that is very easy to test in teeny tiny increments. The only way that I can make code that is easy to test in teeny tiny increments is to make code that is very clearly decoupled. That means that the complexity is down. That means that the malleability is up. So those techniques really help with complexity and help with actually catching defects, early on, having them never get out into production. So yeah, absolutely. So let's get back. So we have escape defects. We need to look at our throughput, or our velocity, if you will, and we need to combine these things. Now, when we combine them, what we get is a ratio, and now we can see if our defect density is increasing or decreasing over a period of time. If you use Rally, they use defect density as escape defects divided by full-time equivalent employees. I'm not sure I actually agree with that as a metric that we can see appropriate trending around, because it's not considering throughput consistency, but that's another discussion. All right, what else results in this? Batch size is a huge issue for a lot of teams, right? The bigger the batch, the greater the risk. We've got this great big batch. That means that there's a lot of stuff that's moving into production. That means that it's risky. We're worried. Because that risk is there, we need to plan more. Because we need to plan more, it takes more time. Because it takes more time, we expect to put more stuff in there. This is a vicious cycle. When we end up with big batches, we end up with actually greater risk. And a batch is everything from the size of the story to the length of the iteration to the frequency of release. You might be writing teeny tiny little stories in 1 week increments, but if you're not releasing them into production except for every 3 months, that's still a huge batch, and that's still a lot of change all at once, and that's still a lot of risk. So what do we want to watch for? Well, we kind of mentioned this. Release frequency is a good proxy for batch size. The reason that it's a decent proxy for batch size is, assuming all other things equal, the team stays roughly the same size, and other factors, the more often we release, the necessarily smaller that release is. So we can effectively use release frequency as a proxy for release size. And in fact, as I mentioned, our release size is a batch size. So if we're releasing more often, that is a good indicator that our batch sizes are going down. And small releases beat big releases every time. We end up with greater optionality, flexibility, learning. We end up with greater safety, right? What's another thing that we can measure across most applications that gives us some indication of batch size? And there's probably a question of like, well, why don't you just use story points? Story points are a batch size. Sure, but they're completely arbitrary, and they can move based on the whim of a team. So I don't do pointing at all anymore. I have found that it does not offer a great deal of value. The conversation is valuable, but the points themselves are not. So if that's on your mind, why not use story size? I don't find it to be as effective as we'd like it to be. But we can look at coupling in the code. Now, coupling refers to the dependencies associated with a piece of code. And there are graphs that can be made. So there's static analysis that will run. It will take a look at the modules in your code, and it'll draw a line between them for every time they communicate with each other. And that communication channel is basically one coupling. Some applications, the coupling is pretty dense, and it starts to look something a little bit like this. Now, what we want, so here we have something that's high coupling. It's two modules. Let's just say that it's a shopping cart and a cash register, right? These two things seem to know an awful lot about each other. So does it make sense that when we change a cash register, we might actually break the shopping cart? Well, it doesn't. It shouldn't, right? They should be able to be independent. But the way that these two things are hooked together right now, there's a good chance that when we change one, we break the other one, right? And there just seems to be a lot of connection paths internally as well, which means that even inside of each of these things, maybe adding an item to the cart, if we make a change to that, it breaks the what's the total value of the cart items or whatever might be in there. So what we want to do first of all with this is we can actually create a simpler interface between them. So keep the two classes complicated, but reduce the number of paths for communication between them. And then we can start peeling apart the stuff inside of that. And eventually we should end up with something that looks a little bit more like this, which is now it's easier to change each of the pieces, and it's easier to change, it's easier to modify this application. Our risk is lower, et cetera. So we can use coupling actually as a way of indicating batch size. If stuff is coupled together, it all has to move together. As stuff is decoupled, it can move independently. All right, what else? Work in progress. We've talked about this one quite a bit. The mantra is stop starting, start finishing. I'm gonna go through this quick. So work in progress. Let's say you've got 4 tasks of 8 hours each. I've got no idea how you know that they're 8 hours. Let's just say that you've got some magic way of actually knowing how long a thing is going to take before you do it. Fine. 4 tasks, 8 hours each. Most people believe that if you start them all at once, you're going to get them done in 32 hours because you've got 4 tasks of 8 hours each. But it turns out that there's actually a tax on context switching. If you're trying to do all of these things a little bit at a time, numerous studies have shown that the tax on that is roughly 20% for each new item. So this is actually compounded, right? So in reality, these 32 hours will actually take you 48.75 hours to complete all 4 tasks. Something to notice here, it turns out that the last time you touch the light blue task, which is the first task you touched, so that task actually completes later than you predicted all of them would be done. The first one completes after you predicted all of them would be done. Right? If we finish them one at a time, it ends up looking like this. All right, I got a couple more. Cumulative flow diagrams. I think these things are super valuable and they're great for diagnostics. So I'm going to run through this quickly. This is what one looks like. Here's how we make one. I don't care what's on this diagram. What I care about is we've got the lanes. We have ready to start, in progress, in testing, ready for approval, and deployed. Yours may differ. That's fine. What we do is every day At some point, you total the number of cards in these columns, or you sum the points, or however you measure your work, drop them into a spreadsheet. You highlight that data and you say, give me a stacked area graph, and you get a cumulative flow diagram. Or more easily, use almost any one of the Agile management tools these days. They all do cumulative flow diagrams. It's going to look something like this. All right. Now, how do we read this thing? That's the work that's been done and the work that's not yet done. That is the work that is currently in progress. I'm counting in progress as dev, testing, and waiting for approval. Right? You might count work in progress differently. That's fine. You can see what your work in progress would look like. So that's helpful information. What else do we have? Well, it turns out that we also can determine the average lead time for a story at any given point in time. From the moment that that story came in to the moment that it was actually moved to done, what is the average lead time? This allows us to start doing some kind of lightweight predictions if we wanted to. We can also see the cycle times for the items in here. Of course, we can see changes in scope as well. All right. So, basic cumulative flow diagram. They tend to go up and to the right. They tend to be nice and smooth. Maybe at least that's what we're hoping for. What I want to do is I want to go back to this diagram that we saw before. And you remember, we had all kinds of reasons that this team was having problems. Everything from ain't got no idea to they're estimating wrong to they've got too much technical debt, et cetera. We had all kinds of speculation around what was wrong with this team. Now, we're going to look at the exact same team. We're going to look at the exact same data. So it's the same underlying data, but we're going to look at it from a different perspective. We're going to go from a velocity graph to a cumulative flow diagram. So we've seen the velocity graph, and we know that we don't know what's the problem. Here's their cumulative flow diagram. I'm going to give you a second to digest this. For most folks, it becomes readily obvious there is a bottleneck in ready for approval. We can see that work is building up, and then all of a sudden, work gets done. And then work builds up, and then all of a sudden work gets done. The challenge with this team, the primary challenge with this team in terms of the variability of their velocity, has nothing to do with how much work is in progress or in testing. The team is doing a good job there. It has to do with the fact that their product owner was a traveling salesperson. And while they were on the road, they didn't have time to review anything. They didn't have time to approve anything, and stuff couldn't go to production without approval. They'd come back into the office, they would approve a bunch of stuff, and they would go, oh, hey, I also learned these things. Here's a bunch of new features I want you to do. And if we look around iteration 8, we can see that the team actually ran out of work entirely, and they actually got new work before their old work was approved, just to make sure that they stayed busy. All right, I've got one last point I want to make in this talk, and that is that metrics are not for managers. More accurately, metrics are not just for managers. Metrics are for teams. We want the team to have the information. We want the team to be able to make the decisions necessary to do their work, to determine how they're going to adjust the way they do things. With that, I want to thank you for your time and your patience and for listening. Again, I mentioned this is from my book, Escape Velocity. You can get it there at that URL. If you want a version of this slide deck and links to all of the resources and research that has been done to support this talk, as well as the book, send a blank email to onbelay@sendyourslides.com with the subject line Escape Velocity. It's all one word crammed together, and it will auto respond with this slide deck and all of the research behind it.